Good morning, everybody. Welcome to another edition of our Power Hour. Today, I will not be presenting. I'm just doing introductions. So we will be talking about logic simulator in our Lua, or Advanced Math Logic module. And today, I'm presenting two new sales engineers that are new to Power Hour. Ben Gratzky's from our systems team, but he's now joined the sales engineering team. And then Saurabh Rajpal, he's just joined us in the last 2-3 months as part of the NovaTech sales engineering team. All right, so Ben, I am going to pass it to you.
Yeah, hello everyone. Again, my name is Ben Gratzky. I'm a NovaTech sales engineer. Today with my co-host Saurabh, we'll be presenting you the updated logic simulator in our Advanced Math Logic protocol. So Advanced Math Logic, if you don't know, uses the Lua programming language. So we'll be doing a little review before we get into the demonstrations. So let's move on. We're going to look at the agenda here. So we're going to talk a little bit about what Lua is itself, just to refresh some of our memories. And then we'll look into the actual Advanced Math Logic port within the NCD program. And then we have a couple demonstrations to share with you. We'll actually step through some of the logic simulator functions just to give you guys a view of what that looks like. And afterwards, we'll have a time period for some questions and answers. And then we have a couple minor things to show you at the end in our last section here. So let's move on to the Lua concepts. So Lua is a lightweight, powerful scripting language. It's been around for a little while. It's been used in a lot of applications which you may or may not know of. We use it for our programming language for our Advanced Math Logic protocol. So that's where that comes into play. So here's just a couple examples of where you may see Lua out in the wild. One of the big ones for me is World of Warcraft. Kind of everyone I know knows what that is. So that's a great example of when people ask me what do I use Lua for. It's used in World of Warcraft. Another good example is Wireshark. We all are probably a little familiar with Wireshark in our industry. Saurabh, you have anything to add?
No, I think, yeah, the space shuttle hazardous gas detection system, they use it for leak detection systems. That's also a pretty good implementation of Lua. But yeah, generally you've covered it all. Thanks, Ben.
Okay, I think we're going to run a quick poll here. We kind of wanted to see what our experience level in the audience is with Lua. Pretty simple poll. Saurabh, you wanna issue that? It's just asking what your experience level is with Lua, basic, or beginner, intermediate, or expert. Just to have an idea of who's in the audience today. We'll let that run for about a minute, give people a chance to respond. Looks like no one's been brave enough to click that expert option. A few more seconds, then we'll share that with everyone. Looks like we're coming in. Yeah, last few seconds here. Looks like we're coming in about 60% beginner, maybe 40% intermediate. You should be able to see that on your screens at this point. All right, that's just to have an idea of where we're all sitting with Lua and our comfort level moving forward. we'll take that into account as we proceed on. So we're going to move into what the advanced method logic port looks like within our NCD program. And for those of you who may not be familiar with NCD, that's NovaTech's configuration director. That's where you set up all of our configuration files for various Orion platforms. Moving on. So once you have an open configuration in your NCD, this is kind of the tree structure you would go down to activate your advanced method logic port. And this is kind of what it looks like when it pops up. Of course, if it's your first time opening up, you won't have any code. You won't have any inputs or outputs assigned. We're not going to get into the details of the advanced method logic port itself. We're going to mostly look at this top bar here, which has the settings and the simulate option. We're going to show you real quick here. There is a settings option here to force all of your logic input points online. They made this an easier access point here. There is a option here to show your numbers. So when you're dealing with a decent number of lines of code, it really helps keeping track, especially in the simulator. It helps keep track of where you are. And you can also customize the font and the color scheme of your background. So as you see, I personally use this cobalt dark setting. It just makes the text pop out a little better for me. Of course, user configurable, so you could do all sorts of crazy color combinations if you're interested. Let's move on. So at that top bar there, once you start the simulation, you have this option to end the simulation. Will pop up on the top of the advanced method logic port, and you have all these other functions that will appear. We'll go through these as we go through the demo as well. So we have the SPI list. That'll be a list of inputs and outputs and logic inputs and logic outputs that you want to track. You can populate that as needed, and you can also use that SPI list to help you force points if you need to while you're doing your testing. You can set breakpoints throughout your code to have the simulator stop, so it gives you extra granularity when you're doing your testing, when you're trying to troubleshoot an issue. You have the option to run your simulator, so you can let it run for any number of as long as you want it to, and you can pause it at any time, and that'll give you kind of a high-level view of what is my code doing. You can see where it's stopped in the process, and you can kind of track what's going on inside the logic. Instead of running the simulator, you can actually step into, over, or out of different functions. This is a more pinpoint level. You could really control what's going on in the simulator and have it step one line at a time in your code and get an idea of what's going on. And we'll go over the options to see the call stack and the variable list. So these show you the actual internal processes of the Lua running your logic. It will show you local and global variables, and it'll show you what the call stack looks like if that's valuable to you. So this next part is just going over some of the options we have in the advanced method logic port. We thought it was important to highlight that there are examples in case you're very new to Lua, the Lua language itself. We have all these Orion functions pre-populated in the advanced method logic port. It's on the bottom left-hand side. And in this example, we've selected the Orion.getPoint function, rather common function we use. And this kind of gives you a use case, a few lines of code to show you how you would use that. It's a good, just a good baseline to get yourself started if it's needed. And so I think we're ready to move into the actual demonstrations. Sarab, I think I will hand it off to you at this point.
Thank you,
We have
Ben.
a couple examples. Yeah. Let me swap it over to you. Take it from here, Sarab.
Thanks, Ben. I'm just gonna start to share my screen. Okay, great, thanks. Okay, so the first example we have is a simple example on a COM fail status using if-else statement. This is a basic setup. You can do it in Logic Pack if you needed to, but we're just showing you the extensive, you can do a lot of things with Lua. So this is just starting from beginning, and we have other examples as well. This simple program monitors the communication failure from two devices using if and else statement. In this example, I have two logical input points, ID1 COM fail and ID2 COM fail, with regards to device 1 and device 2 COM fail statuses, and they are basically ORing into another third logical input into a COM fail point. So these are the three logical inputs that I've created for this example. If you look into the code itself, I have a function COM fail event timer, which runs every second. It can be 3 seconds, 5 seconds to your needs. And in this example, we can see if ID1 COM fail goes high or ID2 COM fail goes high, then we're putting that statuses, if any one of them goes high, set the point to COM fail logic point. And if not, then set the COM fail to 0. It's a simple example, but we use it in quite a bit of in substation and utility automation. Just this example is just a fair small example. This example would not be great in case we have large number of devices, like 30 or 40 devices. In that case, we have another example which could be done using for loop. So in this example, this similar logic can be converted using tables in Lua and for. So I'm defining here a COM fail table with the list of number of devices. I have 5 devices for this example, but it can be 30, 40, 50, as many devices as you can define in this code here. And then I'm calling a function a timer, which runs every second as well. Then I'm asking that, defining a local variable alarm, which is set to false. And for every element in this table, if any one of them is 1, then I'm setting that COM fail table equal to 1. And then I break the for loop. And then I'm also setting up the COM fail logic equal to 1 in case if any one of the ID goes high, and I'm setting it to 0 if it's the reverse. So it's a simple example, but it can be expanded to COM fail. I will show you this example in NCD file. Just bear with me. So for the ease of time, this is a code just I showed you in the slide before, where if and else statement. Again, just to repeat, this is a timer set up here every second, COM fail event 1 timer, every second it runs. And then I'm using 2 devices, any one of them goes high, which means a COM failure is detected from any of these devices. Set that COM fail logic point to high so SCADA can note there is a COM failure. To show that, I'm going to simulate this code here. I also have SPI list pre-cooked already, which basically I can force and see the real-time statuses of these. So ID1 COM fail and ID2 COM fail are currently 0. And so as the point that's going to go to SCADA or EMS system is also 0. So I'm going to run the logic now, and I'm going to force, assuming one of the device goes fail. So I go to the value and then click 1 here, and then force the value. and you would see COM fail picked up, right? Just as per the code, if any one of the device fails, we want the SCADA to be reported as a COM fail. I'm going to remove the force and try on the second device, IAD2 in case goes comms fail. Boom, we can see the COM fail just turned up. So it's a simple logic, but shows you that it can be done easily. Now, the second example that I had using the tables N4, I'm just going to switch my timers. I'm going to make the COM fail event timer. Sorry. Okay. I'm going to make this false and make the other timer true. I'm going to repeat the same thing, but now it's just list of number of devices that are ORed together using the same logic. So I'm going to try to simulate it. We're going to see our spy list pop it in, and I'm going to run the code. And now in this example, I have 5 devices that are currently looking into any COM fail. So I can take any one of them, say ID4 goes COM fail. I'm going to force that. Boom, COM fail automatically goes high. Just removing the force value on that. So just simple example like this, where we can just do basic Lua programs to do COM fails. This was just a demo of if you've got, to conclude, if you've got less number of devices, you can use if and else. If you've got something like, 30, 50 devices or room of expanding in the future, I would probably use code with tables N4. In this code, we don't touch anything in this area. We just add the number of devices and keep on expanding, so we don't have to rewrite the code again. That was the demo on COM fail. I'm gonna move to the third demo. Back to you, Ben, unless you've got something to add on it.
No, that was great, Rob. I think I'm ready to take over for the binary counter here. So we've set up a simple program in Lua. All it's doing is counting up from 0 to 31, and it's every 3 seconds. It's going to update the main count you see at the top, and it's representing the binary bit positions of that count. So this is just a live NCD running on my Rhinolex Plus here in the office. And we're going to go back to the slides now, and we're going to talk a little bit about what that looks like and how we could use Logic Simulator to step through this process to see what's going on. So this is just the starting point here. Little screenshot. So we're going to go into the actual NCD screenshot here and show you what that looks like. So here I have my advanced methodologic port. I have started the simulation, so I have access to the spy list. I have it populated with a couple of the HMI LED points, and these are the points that are turning the actual live HMI screen LEDs off and on. And then also here I have an example of the variables list. And we can see the actual local and global variables running in the Lua program. And so I've got a couple pre-done screens I want to share with you guys, and then we'll actually go into the actual live NCD program. I'll show you what that looks like. So here we've stepped through and ran our onload event function, which is the default start function. We've run our build table sequence. We've gone through that whole thing. And now we can see in our variables list, we have our table populated with attributes 1 through 5. and some information that we need to run the rest of the code. And as you see, there's a little arrow designated where you are in the code. So right now we're on line 41. We're at the tail end of the default start function. And so after the default start function executes, all we have else in the code is the main timer that executes once every second. So we'll see on the next slide here, we're going to move to the main timer function. We've already gone through a sequence. You can tell we're at the end of the main timer function at line 67. And we have a little update here. So the binary value is now 1. We can find it in our table here. The global binary value is 1. And our LEDs are representing the binary state equal to 1, 0, 0, 0, 0, 1. And we'll go over this more in depth. This is just a preview of the demonstration. So this last slide here, this has gone through several iterations through the main timer. So this is probably, 20 something iterations past the previous point. We've done this update several times, and now our binary value is at 7, and our LEDs are representing the binary value 7, 0, 0, 1, 1, 1. And so, yeah, let me switch over to my NCD program here. I have the file open. I have my logic simulator here on the screen, and we're going to start the simulation. So I'm going to click the simulate button here. And so I've used this previously as I was taking some screenshots before. So I have a pre-populated SPI list. All you need to do to populate that SPI list is to drag and drop these values over into this little screen. But since I've done that already, we have these points here. I've added the HMI binary value. So this is the actual value that's being displayed on the HMI screen. And let's see. Let's look at what we have. So here's our variable list. It's actually gone through and run this portion of the code from the top down into the default start function on the onload event, and we're ready to execute the build table function, but we haven't quite got there yet. So let's take an accounting. All these global variables are in our global variable list. We can see that we have our max binary set to value 31, our number of LEDs are set to 5. We have cycle delay set to 3. That represents our 3-second delay. And our binary value and counter start at value 0. So we have to close this variable list. And so now we're going to walk through a couple steps here. So we're ready to go into the build table function. We can hit this run button, and that will run the actual code in real time and process, and we could hit this pause button and have it stop, but we don't really have any control over how much get processed. We can set some breakpoints, but this runtime just kind of executes the code and goes until you hit the pause button. So if you want to be more low level and have a little bit of a control over what we're doing, we can hit this step into function. So we're gonna execute. This is going to take us into this line of code and execute this. So that's going to go into this function build table. And so you see it hops around the code a little bit. So now we're in our build table function here. And as we showed you guys before, we're running a little for loop here. The plan is to go from 1 to 5, the number of LEDs, and we're going to populate our count table with some information that'll be useful for us later on. And so just to reiterate, we have count table as a global variable. We can see it here in our list, count table, but there's nothing in it. It's just an empty table right now. So we're gonna populate that with some values, and we're gonna step through a couple lines of code here. We're gonna let it go through this first line of for loop. So we're at the count table. Let's see where we are. We are at I equals 1, so that's our iterator. So we're ready to step into this for loop and start populating count table at attribute 1. So let's take a couple steps. It's going to populate that HMI attribute, the power attribute, and now that we're back at the for loop, we should see that we're at I equals 1 still. We haven't quite got past that. But if we look at our variable list, we are just past that first iteration of the for loop, and we can see that we have an attribute of 1. And that has some information. The power is equal to 1, so that's kind of the two's power of that first LED. Its value is 1 in binary terms. And then the point that's associated with that LED is HMI LED 1 at logic. And that's the same point name structure as here. We're going to use that in when we update these points. Makes the code a little bit cleaner. And so let's accelerate. Let's go through another iteration and we'll see it populate. We're going step by step. It's doing this, it's doing this. We're at the end of that for loop. So we've gone through the for loop. We can look at our variable list again. Our index is 2. And if we look at our count table, we can see that we have 2 attributes now. We have 1 and 2. So 1 is the same, that hasn't changed. 2, we've added, it's 2 to the first power for this one. So that's a value of 2. And then that's tied to HMI LED 2 at logic. And so not to belabor it, but we're going to go, so say we're done examining this part of the code. We want to skip ahead a little bit and go to the end of build table. So let's go straight to the step out of function. So this should process all of that. And notice our pointer is now here at the end of build table. So we kind of did this entire bit. We did I equals 3, I equals 4, I equals 5, exited the build table function. Now we're at the end of the onload event, and we can check our status. So you notice, since we're not in that build table function, we've lost our iterator. That's disappeared. It was a local variable. That's gone now. We have our count table. We have attributes 1 through 5, and this will be all the information we need to run the rest of our program. And so from here on out, we're going to go into the main timer, because the only other process that's running is the main timer event. We could confirm that by looking at the events tab. We have a default start function that's run at load time, and we have a main function that's a timer that's run every 1 second. And so now in the simulator, if I step forward 1 step, we're going to go straight to the main timer. So this is the first execution of the main timer code in the simulation. And just to briefly explain what's going on here, we have the cycle delay. If you hover over, you can see that cycle delay is set to 3. That's a 3-second delay. So there'll be 3 cycles, 3 loops of the main timer that don't really do anything. We're gonna increment this count value until counter is equal to 3. We're gonna ignore this portion of the code. So on this first run through, counter is 0, cycle delay is 3. 0 is not greater than or equal to 3. So we're going to skip down to this portion of the else statement here. And this is just incrementing that counter variable. So let's see how that works. It's going to evaluate this if statement. It's going to kick us out because this evaluates to false. So we go to the else. Now counter is 0. We're going to update that value with counter plus 1. So after it executes this line at 64, we will see counter is now set to 1. And we can always confirm that by looking at the variable list. And we can see that our counter value is 1. So in order to execute this, so we see that binary value actually increments to 1, we have to do this a couple times. We do this loop a couple times. So let's step out of the function. This should run a whole other process for us. We're back to 67. Oh, it put me in the runtime. I was not expecting it to do that. Let's pause it. Let's okay, so that actually put us into runtime mode. So we actually accelerated ahead a couple iterations here. And if you notice, we've actually updated our binary value. So our binary value is gone. So we've done 10 or so iterations to go through those steps. And to take accounting here, so right now our counter value is 2. So we're in the process of updating the binary value to go from 3 to 4. We'll do that in slow motion this time to see the process. But here we have, so binary value is 3. We've run our update, so we have our HMI binary value is now 3, and then these LEDs should represent the binary representation of 3, so 0, 0, 0, 1, 1. And that's what is displayed on the screen. So let's go slow motion this time. Our counter is about to be incremented. So now counter is going to be equal to 3. There it is. Counter is equal to 3. So on the next run through, counter is 3. The cycle delay is 3. So we're going to go into this portion here. So one more step, we should see it advance to line 54. There we are. And so this is a double check. Once we hit 31, we want to reset back to 0. We are not going to do this, so that this is going to evaluate to false because right now the binary value is 3. So we'll go down to this line 57. And here we have binary value 3, and we're just going to increment it one tick to 4. So once that executes, binary value is equal to 4. We could confirm that again in the variable list here. Binary value equals 4. Important for the next run through, the first thing we want to do is reset this counter back to 0. So we can count up again to 3 to implement our 3-second delay. So this next step, counter is now equal to 3. All this does is make that counter variable 0. And hover over here, counter equals 0. And now we're going to execute this update HMI function I wrote. So this is going to update all of these LEDs appropriately because now our binary value is actually 4. So we have to update these HMI variables. So one step in takes us to the binary, update binary HMI. And this is a little script that goes through, sequentially sets these LED values appropriately. It's doing a little bit of binary calculations to determine what the individual bit settings are. And this set point here is just setting this binary value into the HMI display. So once this runs, we should see this SPI list update to HMI binary value 4. So we're going to run that process. There we go. We have 4 in our HMI binary value at logic point, which is again going to be on our display. And so here we're doing a little reverse for loop. So we're going to start at 5, work our way down to 1. We're going to increment by -1 every time, and we're going to populate these one at a time. So what do we expect to see for this case, a binary value 4? We're going to expect to see 0, 0, 1, 0, 0. So we're going to run through this. And if at any point in here you're asking yourself, where am I in this for loop? You can always look at the SPI list, at the variable SPI list, and see my index is at 5, my step is -1. I'm actually at I equals 5 right now. It has some local variables here it's using for tracking. So I've actually loaded this temp because I'm using this to determine if that individual bit is high or low. And after we step through line 95, we'll see that we have a local variable called bit, and that is loaded with what we should load into this HMI LED 5 at logic point. It's already a 0, so we're not going to see that actually update. But let's go through a couple steps here. It's going to skip down to this portion, set that to 0. And so now for this third one, we should see that we're on the I equals 3 iteration of the for loop. So that's going to be looking at this HMI LED logic, HMI LED 3 at logic point. We should expect this to turn into a 1 at this point. So after it does a little processing, let's look at our bit. So bit is now equal to 1. So that means we're going to load a 1 into this HMI LED 3 at logic point right now. So let's accelerate there. So if bit equals 1, we should expect this pointer to go down to 97. Here we are, 97. We're about to set this third value. So let's go one more, and we'll see this update. So that's a 1. And we decrement this temp just to keep track of our binary logic. And then now we're at the next iteration of a for loop. So that's going to be I equals 2. Remember, we're going backwards. So here's I equals 2. So we expect HMI LED 2 and HMI LED 1 to be set to zeros to represent our binary 4-bit string. So we go through this process, and we could probably float over here. You don't have to pop open that variable list. You could look at here. So bit is going to be 0. So we're expecting this HMI LED 2 to be set with a 0. So let's step through that. We're pointing at 100, which is our setting for 0. So once this runs, we'll see that updates. And then one more time, real quick, we're expecting this to evaluate to be 0. Kind of hover over it, bit equals 0. We're going to see this set to 0. And now that we're back to the for loop, it's gonna kick us out of the for loop because we've done all 5 of our iterations. We're at the end of our update binary HMI function. Once we hit advanced, we're gonna go back to our main timer. So we're all the way here at the end of our main timer, and we're done with that entire sequence. We've updated our HMI values, so we should see the binary 4 and the 00100 string. So I'm going to go to the actual live HMI page here. Just to reiterate, so this is what you see with all those HMI variables. So this is the binary count that we're updating, and these are the LEDs turning on and off as everything gets updated. And you know, if the timing is right, it updates about every 3 seconds. So that's pretty much the extent of the logic simulator demonstration we had prepared for you guys. Saurabh, any words, any comments you want to add here?
I think it was a fantastic job, Ben. I think this is great. We can probably take questions, if any, on this particular demo or in general. We can give a few minutes on that, and if not, then we can go to the second poll.
Oh yeah, I see a comment from Janet Haynes about maximizing my window. Sorry if the logic was a little too small for you to see. I don't see any questions coming in. Yeah, if there's nothing else, we had a poll put together at the end here. We just kind of wanted to see some feedback of what you would like to see in a future Power Hour, Lua focused Power Hour, I should say. We have a couple options here, or if you have something else in mind, you can feel free to add it to the chat or email one of us, and yeah, we'll take that as input as well. Saurabh, you want to run that poll?
Yep, it's right now. It should be on for all the users to select what would they like to see in Advanced Lua Power Hour. The
Okay.
options are cap bank controller, something on redundancy with active and standby, automatic report generation, microgrid controller, or other. If it's other, please feel free to drop in a comment box or question box.
Yeah, please feel free if you have any questions. It looks like we're getting a couple coming in. Let me take a look. Okay, looks like Tim has used the logic simulator to his advantage and figured out one of his issues. So that's great feedback. Thank you, Tim.
Okay, I think the poll, I'm going to close the poll now and share the results. So it seems like the audience wants to know more on Orion redundancy logic the most, and then a tie between cap bank controller and automatic report generation. And few of them, 17% did say about microgrid controller. So that's great.
We had a comment about setting the breakpoints. Oh, sorry, I'm getting an echo. So there is the option to set breakpoints. So as you see, I've set a breakpoint here. It's kind of difficult to see, but it's this red circle. So that'll be an additional ending point when you're stepping through the logic. If that makes sense, you should be able to click on this that breakpoint, and you have the option to clear all your breakpoints. So if I click on that button, it goes away. So I believe if you toggle the breakpoint, yeah. So there, I could set this. So if I want to set a breakpoint down here, I can set another breakpoint. So these are just additional stopping points. So I believe when you step out of the function, this will force the simulator to stop at those points. You know, it gives you extra levels of granularity when you're looking for specific issues or problems you're having. Just going down the list here. Okay, we'll run that. Yeah, so here we've encountered this, and it stops at our breakpoint. So that's just an example. So if we want to do another loop, we hit runtime, it goes to another loop, and then we stop here. Yeah, so on that note, so Eric Penny's asking if it's possible to change the online state of a logic point created to offline. So the way you do that is in the actual set points function. So let's look at, so we'll end the simulation here. I'll show you that feature. So when you're setting a point using Orion.setPoint, you actually have the ability to set the online status of that point with this attribute online. So you can just set online equals false, and that would turn that point to be offline. That's what comes to mind as an initial response to that. Well, have you shared the results of the poll, Saurabh? That's already done?
Yes, that's already done, and we can always send it out as part of the presentation. Yeah.
Okay. Yeah, it looks like there's a plurality of people asking for the Orion redundancy logic, but there's also interest in the report generation and our version of a capacitor bank controller. Yeah, so looks like we might have a couple upcoming topics to present. Well, if there's no more comments, I guess let's flip back here to our slides. So we just had a couple slides here to share with you guys, just some things that NovaTech has. We have some previous Power Hour links here. to similar topics involving advanced math logic and Lua. And then we have access, some links to our libraries and other resources we have available. And we also included this online compiler that some of us use when we're just kind of prototyping some code. It's nice. It's a nice, quick way to make sure that you're on the right track when you're coming up with a new block of code. Make sure it's functioning the right way. Here's our customer community website. We have documentation, our NCD programs accessible from this site. All of our previous power hours are also accessible through the community website. And then we have our customer support site. This is where we could exchange files with you. If you have a troubleshooting issue, you could load up your file here, get some detailed CAD drawings or various product lines, firmware updates. Everything's here on the support site. It is a new interface, so if you haven't been here for a while, it's going to look a little bit different, a little bit modernized. I think that's all I have to say about that. We have on booking.novatechautomation.com, you can come here and book some time with any of us sales engineers at NovaTech. Here's a list of us. You can request anyone, or you can request a specific individual if you have certain needs, or if you've been working with a certain person in particular, you could request their time, set up a time and date, and we will be notified. And we're here to help you. So I think that's the end of the slide deck. Again, I'm Ben Gratsky. My co-host has been Sarab. We are available. Feel free to email us with questions, concerns, comments. I think that wraps us up.
Thanks, Ben.
Oh, let's
Thanks,
see.
Rob. Thanks,
We got a
everyone, for
couple.
attending. Oh, anything else, Ben?
Oh no, someone just sent a question. I was gonna get it last second here. Can you import log? Yeah. So to Eric's question here, he's asking, can you import Lua logic from another config file? So there are ways to make that easier. That might be a good topic. That's something we call using Lua library files. So that's an easy way. There is always going to be some setup work in setting up your logic inputs, your logic outputs, but there are methods to incorporate previously written code into an existing NCD file. Sorry, Chi. That's all I have to say about that.
Yeah, so that could be, something that we can talk in the future power hours, or Eric, if you would like to reach out to Ben or Sarab in the booking site, they can go through that with you directly as well. Thank you, everyone, for joining today. We are taking a little break in December for Power Hour just because of the holidays. So we will see you in the new year. So have a great rest of the year, and we will talk to you soon. Thank you, everybody. Bye-bye.